Good morning. I'm Dr. Vinita Mathur from JCRC Jaipur. In previous classes, we have seen about operational amplifier basics and its pin configuration. Today, we will be seeing its applications in the form of differentiator and integrator. So let us have a recap. The operational amplifier, abbreviated as op-amp, is a versatile building block that can be used for realizing several electronic circuits. They have differential amplifiers and their output voltage is proportional to the difference of the two input voltages. This is the schematic symbol, which consists of two input terminals called the inverting and non-inverting, which are labeled with minus and plus respectively. It has two supply voltages and an output terminal. To analyze these type of circuits, we first check for negative feedback to ensure that an increase in the output makes the inverting and non-inverting terminals difference decrease, and the output is connected to the inverting terminal. Next, we assume that the inverting and non-inverting voltages are equal. Why? Because the gain is considered as ideal, so it requires a negative feedback. We assume a zero input current in most of these circuits. The current at the input terminals is very small in the range of nanoamperes. So we consider it as zero. We apply KCL at each op-amp input node separately, but KCL is not applied at the output node because it is unknown. So let us start with an integrator. Integrator means it will integrate a lot of things in one. Differentiator will differentiate into a lot of fragments. The integrator produces an output voltage across the op-amp, which is directly proportional to the integral of the input voltage. But here, the duration of input signal is also considered as it performs mathematical integration with respect to time. This is the diagram for an integrator. Let us first understand its working. The construction uses an operational amplifier along with two passive components. The components are resistor and capacitor. These resistor and capacitor form a first order low pass filter. Integrator is exactly opposite to that of the differentiator. Here, the feedback resistor is a capacitor. The resistor and the capacitor, they are connected across the amplifier, which is in the inverting configuration. As we've already seen that the gain is infinite, therefore the inverting input of the amplifier is a virtual ground. When a voltage is applied across the resistor, the current starts to flow through the resistor as the capacitor has very low resistance, which is insignificant. At this situation, if the amplifier gain ratio is calculated, the result will be less than unity. Let us see here. The gain ratio is taken as XC by R, which is very small. As we can see here in the note I have written that for the inverting amplifier, the gain is equals to output by input, which we have seen already in the previous classes, which is equals to the minus of feedback resistor by the input resistor. Here, in case of integrator, the feedback resistor is what? Capacitor. And input side it is the resistor. So this gain ratio is very small. The capacitor begins to charge up by the input voltage, and in the same ratio, the capacitor impedance also starts to increase. This charging rate is determined by the RC time constant of R and C. The virtual earth now hampered and the negative feedback, it produces an output voltage across the op-amp to maintain the virtual earth conditions across the input. Let us see now, how do we calculate the output voltage of the op-amp? I have again redrawn the circuit for the reference. IR is the current flowing through the resistance. IF is the current which is flowing through the capacitor, which is the feedback current. X here is the virtual ground. Let us apply KCL across the junction. So IR is equals to the current flowing in this inverting terminal plus this IF current. But as we know that it is an ideal op-amp and X is a virtual ground, so no current will be flowing through the inverting terminal. Therefore, the inverting terminal current is equals to 0. So from the previous equation, we come out to be the resistor current is equals to the feedback current, which is the current flowing in the capacitor. The capacitor has a voltage current relationship which has the formula IC is equals to the capacitor dVc by dt. Now let us apply this formula in our practical scenario. Let us see this diagram again for the reference. Vin minus 0 x, which is the virtual ground, divided by the resistor, is equals to C d 0 again is the virtual ground minus V out by dt. This is the current across the capacitor. This is equals to 0 we have eliminated, and we are integrating both the sides. Why are we integrating both the sides? Because we need to remove this differentiation d by dt here, and we need certain limits here, which is 0 to t. So the ideal output voltage of an op-amp integrator comes out to be V out is equals to minus 1 by RC, integration limits from 0 to 2, V in by dt. So we can say that in an integrator, the output voltage is the integration of the input voltage. However, there are certain drawbacks of integrator. The capacitor blocks the DC, and due to this, the DC gain of the op-amp circuit become infinite. Therefore, any DC voltage at the op-amp input saturates the output. And to overcome this problem, a resistance is added in parallel with the capacitor. This resistor limits the DC gain of the circuit. The output behavior of an integrator amplifier is different in each case of sine, square, or a triangular waveform. So what are the applications of this integrator? It is an important part of the instrumentation, which is used in ramp generation, used in function generator to produce the triangular waveform. It is used in wave shaping circuit, such as a different kind of charge amplifier. And yes, in analog computers also, where integration is needed to be done using the analog circuit. It is widely used in analog to the digital converter. There are different sensors used as an integrator to reproduce the useful outputs. What is a differentiator? As its name implies, it performs an operation of differentiation. That is, it produces an output voltage which is proportional to the input voltage rate of change with respect to time. The faster or larger the change to the input voltage, the greater the input current, the greater will be the output current, which becomes more of a spike in shape. A differentiator with only RC network is called as a passive differentiator, but here we have operational amplifier also, so it is an active differentiation. Let us have a look at the diagram of a differentiator. Here we have a resistor as a feedback, and at the input side we have a capacitor. You can relate to the previous slides. It is just the reciprocal or the inverter of the integrator. By exchanging the positions of resistor and capacitor in integrator, the differentiator circuit is obtained. Very easy. So in this input signal is applied to the capacitor. See here, again for the reference, the diagram is redrawn. The input here in this case is applied to the capacitor. Now this capacitor blocks the DC content. So there is no current flow in the amplifying summing point, and the resulting is the zero output voltage. But it allows the AC type input voltage to pass through, and whose frequency is dependent on the rate of change of the input signal. In this circuit, we have applied some input signal, and the current IC is flowing through this capacitor. We are assuming that our op-amp is an ideal, so no current will be flowing inside this operational amplifier. However, a current in the range of nanoamperes flow, which is considered as negligible. Now, because of this negative feedback, this node will act as this X point acts as a virtual ground. The potential at this node will be 0 volts. Let us calculate the output voltage now. Same notations we have used. IF is the current flowing through the resistor. IC is the current flowing through the capacitor. X is the virtual ground, and we have applied the KCL at this X node. So the current across the capacitor is equals to the inverting current plus the IF current. Since it is an ideal op-amp, so the inverting terminal current is taken as 0. And again, as we know in previous, we have seen that the current voltage relationship in a capacitor is given by IC is equals to C dVc by dt. We have substituted this in our formula and we find that the output voltage is equals to minus times RF capacitor dVn by dt. That is, it shows that the output voltage is the derivative of the input voltage. There are still some drawbacks of differentiator. The gain increases as the frequency increases. Thus, at high frequencies, they become unstable and break into oscillations. Also, the input impedance decreases as frequency increases. This makes the circuit very much sensitive to the noise. Hence, because of these limitations of stability and noise problems at high frequency, we use a practical differentiator wherein we add across this resistor, we add a parallel capacitor. Where do we use these differentiator? They are mostly designed to operate on triangular and rectangular signals. They also find application as wave shaping circuits to detect high frequency components in the input signal. Thank you.